Hi, I'm John Paul Raj, and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. This is part 5 of continuous functions. And on this video, we're going to talk about intermediate value theorem. Let's start. In my opinion, the intermediate value theorem is a very basic, fundamental idea in calculus that often gets overlooked. Okay, it's one of those people in our lives that sometimes unintentionally we take them for granted, but their presence is vital. Without them, a lot of things probably don't get done in our lives. Okay, and in the same way, I think the intermediate value theorem is one of those properties, one of those theorems without which a lot of things in calculus probably would not be even possible. So what is the intermediate value theorem? There are three important conditions for this theorem to be true, okay? So we'll say if f of x is continuous on the closed interval AB, second condition, and if that f of a is not equal to f of b, that means the value of the function at the left-hand point of the interval is not equal to the value of the function at the right-hand point of the interval. And the third condition is that there is some k, some value k, such that k is in between that fb and that f of a. So these are the three conditions. This is only the condition we're talking about here, okay? If fx is a continuous function on the closed interval ab, can you guys see this? If the value of the function is not equal, all right, at the endpoints, f of a is not equal to the value of the function at the right endpoint, and if there is some k in between those two values, then what's going to happen? Then what the intermediate value theorem promises us is this, all right? Then there is at least one c in between. That c is going to be in between that a and b, all right? Such that the value of the function at c will be equal to that k, all right? This is a very interesting promise that the intermediate value theorem says, okay? It says that if the function is continuous on the closed interval ab, if the value of the function at the two endpoints are not equal, and if there's some k in between that fa and fb, then the intermediate value theorem literally guarantees us that there is going to be at least one c in that open interval a, in the closed interval ab, sorry, where the value of the function is going to be equal to that k that we were talking about. Let me illustrate this, okay? Because sometimes illustration really helps in understanding what this text is all about, all right? So I'm going to draw a graph here. Let me get the grid first. Okay, that's an interesting grid. Let me just get it right. Here we go. Can we see this? All right, now that's going to be my x-axis, the y-axis, and I'm going to draw a graph. Remember, this is a closed interval, so that's included, and this is going to be my b, this is going to be my a, this is here my f of a, and this is going to be my f of b. All right, so what conditions are satisfied so far? F is continuous, we can see on the closed interval ab, that's correct. And then what do we want? F of a is not equal to f of b, that's our f of a here, and that's our f of b there. They're not equal, they're far apart. It says, and if there's some k in between fa and fb, so there's some k in between fa and, you're looking at the y values here, right? Y values, some k in between fa and fb. So let me just mark that with some of the point, some of the color here. Let me take a value here, okay? Let that be k. Some k in between fa and fb, the y values. What the intermediate value theorem is actually promising us is that there should be some c in among the x values, okay? There should be some c among the x values in between a and b, where the value of the function is going, that's going to be our c. Can you see that? All right, where the value of the function is going to be equal to that k. It feels very obvious that you have a function that is continuous over a closed interval, which means it's taking every value in between fa and fb. Every real number between fa and fb takes every value. So if at random you pick up any value in between fa and fb, like this k, let's just call this thing like, let's call it p, all right? So if p is a value, a y value in between fa and fb, then its corresponding x value will be exactly somewhere in between a and b. That's what this theorem says. Seems obvious? Well, let's take an example, all right? Here we go. This is an example. It says, can you guys see the question? It says, below is a table of values of a continuous function f. Use this table to answer the questions. All right. So we've got x values in the first row, y values f of x, the y values in the second row. All right. And it says on the interval 3 to 7, must there be a value of x for which f of x is equal to 5? And explain. All right. We see that the domain has values 3, 4, 5, 6, 7. All right. So from 3 to 7. And remember, they said it's a continuous function. All right. Continuous function means it's going to take all values in between 3 and 4. It's not going to jump from 3 to 4. All values in between 3 and 4. Okay. Likewise, all values in between 4 and 5. All values between 5 and 6. I'm talking all real numbers between 5 and 6. All real numbers in between 6 and 7. That means all real numbers from 3 to 7 is part of the domain. And likewise, all real numbers from 4 to 6 is going to be part of the range. Okay. Continuous all values. So in that context, the question is, on the interval 3 to 7, must there be a value of x for which the range, there is a value called 5 in the range, okay? F of x is equal to 5. So when we look at the range from 4, it drops down to 1. Remember, all real numbers, okay, dropping down to 1. From 1, it drops down to -3. So all real numbers between 1 and -3. And then from -3, it climbs back to -1. And then from -1, it climbs back to 6. Now, because it is continuous, every value in between -1 and 6, the function will take. That means there must be a value 5 because it can't jump from -1 to 6 just like that. It must pass through 5. And that is the explanation. So you say by intermediate value theorem, we can be sure it guarantees that there must be a value. We don't know what that value of x is, but there must be some c in between 3 and 7 where f of c would be equal to 5. That is what that intermediate value theorem can guarantee. That's why it's powerful, okay? That's why it's powerful. Let's look at the other question here, 21, all right? It says, on the interval 3 to 7, could there be a value? Look at these words, okay? Could there be a value for which the value of the function is 7? Now, we know the question says that the function is continuous from 3 to 7. Okay, x value is 3 to 7 and the values of the function are going from 4 to 6. What happens after 6? That has not been guaranteed by the intermediate value theorem. So there is no such guarantee. So we said we can't be sure. It says, could there be? It could be, but we can't be definitely sure. We can't be 100% sure. And that is what we want to say. Okay, so we'll say that we cannot say with certainty. That is the difference. Okay, we cannot say with certainty. That's the key word. We can't say with certainty. This thing we can guarantee because the function is continuous, and which means it's not going to jump from -1 to 6. Okay, it's going to take every real number in between -1 to 6, which means 5 is included. But the number 7 comes after 6. So intermediate theorem can only be applied to this table and not for values outside of this table. So the word is certainty. We cannot say with certainty that there is some x where f of x is going to be equal to 7, because 7 is not part of the table, and we only have information that the function is continuous between 3 and 7. X values 3 and 7, but the y values are going from 4 to 6. Okay, and 7 lies outside of that range, and we cannot comment on that with certainty, that is. Okay, let's look at the third part of this question. It says, what is the minimum number of zeros? Can you guys see this question? What is the minimum number of zeros f must have, guarantee, must have on the interval 3 to 7, the same interval we're looking at? What's the minimum number of zeros? Again, must, a kind of guarantee. That's what the intermediate value theorem is teaching us. Okay, so if you look at it, look at the signs, okay? The signs positive, negative of f of x. F is positive. You cannot have a continuous function that goes from positive to a negative value without going through 0. So there must be 1 0 here. All right. Now again, look at here. This is negative to negative, continuous. That's fine. And again, there is a sign change from -1 to 6. Okay. From negative to positive, there must be 1 0 here. Why? Because the function is continuous, and using intermediate value theorem, you have to have every value in between, and 0 comes between a negative and a positive value. So the minimum number of zeros that the intermediate value theorem guarantees is 2 based on the information that is given to us. The reason we say minimum is because it can cut through many more times. I mean, we don't know what's happening because we don't know the intermediate value, right? From when the function value is 1 and then it's going down to -3, it might have cut down maybe 2 or 3 more times. We don't know. But from the information that's given to us on this table, the intermediate value theorem guarantees us a minimum of 2 zeros. I hope that this video helped you understand intermediate value theorem. I'm going to see you all in the next video.